Hello. The signals that we've been using so far in our analysis have largely been fairly rudimentary. Sinusoids, complex exponentials, decaying exponentials, impulses, unit steps, and the like. These are described simply with mathematical equations, but they may not be useful in describing some of the signals we encounter in real life. In fact, a lot of signals vary in very complicated ways and just plain aren't expressible with simple equations. So a lot of signals also can be considered noise. And so this drives us to start looking at the class of signals we call random. Now, random signals include noise, but they could include a variety of other things. For example, a speech recognizer describes speech as noise. Every little bit of speech has a particular characteristic to it, but every time you say the same thing, it comes out slightly differently, it's picked up slightly differently, and so it can be considered noise with a pattern, you might say. Well, all of this can be encompassed in the discussion of random signals. So we are going to describe a random process as an index set of random variables, and each of which is characterized by a cumulative density function, or CDF, or probability density function, or in the case of discrete valued random variables, a probability mass function. So a CDF would look somewhat like this. The probability, and we're showing that this is the CDF pertaining to the random variable x of n, and we pass it an argument. In this case, it's a specific x of n corresponding to a specific n is equal to the probability, and I apologize for the notation here because often probability is denoted by a capital P, and sometimes we need to get this from context. Maybe it will help to know that we usually don't use CDFs. We usually use the PDF. So it's equal to the probability that x, the random variable, is less than or equal to the x value, x of n value that we put in there. This can be expressed in terms of the PDF by integrating the PDF. This is with a lowercase p, I should put in a dummy here. Let's do u of n, n, d u of n. So, because, as I've expressed before, my square brackets never quite look like square brackets, and we're going to be using a lot of them in this section, and also to be consistent with common notation in the field, I'll use x sub n for xn in this section. Okay. So one thing to note is that the PDF and the associated CDF for this random process x of n is defined for every n. In other words, at every point in time, we could have a different probability density function. Let me give you a good example of where that might come into play. Let's suppose that we used a microphone to pick up the beep from a UPS truck as it backed up. But there's other things going on. And so what we end up getting is a pure tone like we would expect for the beep coming out of that truck, plus some noise. So what does that mean? That means that every single sample that we pick up is going to have a different mean. What is the mean? The mean would be corresponding to the underlying perfect tone, and the variance would correspond to the noise added to that that causes the observed tone to vary from a pure tone. So in this case, every single sample has a different mean, and what we have is a random process, a random signal, but a random signal with some structure and shape. So that's all well and good, but in this particular example, you can see that each of these signals is related somewhat to each other. So if we were to grab two adjacent samples from our noisy beep, we would expect those adjacent samples to be close to each other, much more so than if we grabbed a sample, say, from right here and another one from right here. Those are going to be far different from each other. So how do we capture this similarity that gives us the structure of the signal? That comes in a joint CDF or joint PDF. So a joint CDF is defined as the probability, and here we use x, n, and at a different index, x of m, and now we have our inputs. That's equal to the probability that xn is less than or equal to our non-bolded xn and xm is less than or equal to our probe value xm. So if we want to go from a CDF to a PDF, we can take our CDF and differentiate it. So for example, let's assume we had something like this for CDF 0. The maximum value here is going to be 1, and maybe this is the CDF for a particular x naught. So let's put p x naught. We take the derivative, and we get the PDF. And the PDF is what people, I think, are used to seeing the most. In this particular case, we're going to get something kind of like that by design. So this is our PDF, and it would be given by little p of x naught, and that would be our probability density function. So the probability density function tells us where a value is most likely to lie. Now with a continuous value, of course, the probability of any particular value showing up is 0. To find the probability that something shows up in a range, we integrate over that range. Or, since the CDF is the integral of the PDF, we take the difference between the CDF at the top and the bottom of the range. Okay, next we're going to discuss a concept which is, I think, difficult or requires a little bit of thinking. When you get down to it, it's not too bad. It's just that, well, let's proceed and see how it comes out. What we've described when we describe the probability of something is the generality of how these signals may manifest. But anytime we observe a real sequence, for example, we observed up above that beep that came from our UPS truck. If we were to observe that UPS truck making the same beep again, it would look approximately the same, but the fine details would all be different. The noise would be different. If we were to do this again, we would see our tone with different noise added to it. And every time it will be different. But every time it will look similar. So, each observation, or as we'll put here, each random sequence is one realization or sample function of the random process. So, a set of realizations is called an ensemble. So, for example, every time, let's do this in black. Every time we observe a particular random process and actually get an observation of it, it might look different. In fact, it will look different. That's the whole point of having random things. So this would be x of n as a function of n, maybe that's 0. And the next time we observe this, we will get something different. So each of these would be realizations of our random process. And together, along with all other implementations that we could get, they could form an ensemble. Now, this matters because we are often, we talk about a random process, we talk about the average of random process, and we need to realize that every particular instance of the random process is just as you may think, kind of reflects Plato's ideals. Somewhere in the sky is the perfect implementation of this random process, and what we see is just a reflection of that. Well, I won't wander too far into philosophy because I didn't study Plato very much. But this will come up later, and we'll next talk about expectations.